All right, in this video, I am working through some of the material in the atoms and light handout. Although a lot of what we're going to be doing isn't specifically dealing with light, your what we do will be certainly very relevant to light, and you'll be using these kind of ideas as you work your project. So the basic thing that's going on here is we add to our Hamiltonian for the atom, we add some time-dependent perturbation. And so it might be something like E Z E of t, for example, if we were talking about light. We know that if V is 0, then if we start out in an eigenstate of H, let's call that G. The only thing that would happen is that we would have a de Broglie phase factor. And so when V is not 0, we're going to assume psi is G e to the minus e g t over h bar. And then in general, other eigenstates of H0 will appear, and we're going to give them an amplitude ck and a similar kind of de Broglie phase factor. Okay, so now now what we want to do is we want to solve the Schrodinger equation, and so we have IH bar and we have psi dot, and so that's H0 psi plus V psi. And now let's operate on the left with state K. And okay, in the first term here, we know that that is going to be E sub k times k psi. And the second term, this kV psi, well, if V is a perturbation, then psi is only going to be slightly different than G, so we can approximate psi by G e to the minus I e g t over h bar. Okay, so we've got the right-hand side there. Let's work on the left-hand side a little bit. The time derivative of the kth projection of psi would be the time derivative of this stuff. So that's going to be I h bar ck dot minus I e k over h bar c sub k, and I left myself insufficient room there. E to the minus I E sub k t over h bar. And similarly, this k psi is ck e to the minus ek t over h bar. And you can see the purpose of these e to the minus I ek t over h bar terms is that these two things, these two terms are going to cancel. And so that gives us I ck dot equals v k g. What we're doing is multiplying through by e to the plus I ek t over h bar. So we get an e to the I omega k g t for the right-hand side, where omega kg is our Bohr condition, h bar omega kg equals ek minus eg. All right, and so now that if we want to solve our equation here, that implies that c sub k, oh, I forgot an h bar over here, is integral 0 to t v kg e to the I omega kg t, and we need a I h bar. All right, so really that is a Fourier transform, because we can assume that what's going to happen in the future doesn't matter. So VKG at, these should be t primes here, and I need a dt prime. VKG of t prime t prime greater than t is 0, and VKG of t prime less than 0 is also 0. And so that means that we can replace the limits on that integral from minus infinity to infinity, and we get a Fourier transform. So CK equals VKG tilde of omega kg and divided by h bar. So the other day we did the example VKG equal to constant, and so when we did that, we got CK, let's just go ahead and get its square. So the probability of finding the atom in state K is VKG quantity squared over h bar squared times t squared times sinc squared of omega k g t over 2. And so then the idea there is that if we plot this as a function of omega kg, we have something centered at 0 and a function that looks like this. And the first 0 out here is when omega kgt over 2 is about pi. And so that's about the width. If we think of this, the x-axis here is omega kg times t. Well, basically, what this is saying is that if we excite a state k that has a Bohr frequency omega kg, we have to do that with a perturbation that's on for a very short amount of time, so that omega kgt is pi or less. If it's bigger than pi or so, there's just not going to be any probability of excitation. Basically, that's energy conservation. That's saying in order to change the energy of the atom or the system by an appreciable amount, we have to apply a very short interaction. All right, so let's do a second example. And this one is more like light. B of t is a constant cosine omega t. All right, so let's think about this. We want to calculate the Fourier transform and evaluate that at frequency omega kg, at the Bohr frequency. And so that's going to be integral 0 to t v, and then we have our cosine omega t and e to the I omega k g t, and that's it. And I better put t prime here. And we're integrating 0 to t. Now, if we look at this cosine, write that as e to the I omega t I omega t plus e to the minus I omega t over 2, then you can see that our Fourier transform is exactly what we would have had before. Except we replace omega kg by either omega kg plus omega or omega kg minus omega, and we get a half. Now, let's assume EK is greater than EG. So this would be the case where, say, the atom starts in the ground state, G for ground, and we're figuring out what's the probability that the atom will end up in the excited state, EK, which is a higher energy. Then our answer here is going to be, going back to the previous thing, remember, we're now going to replace omega kg by omega kg plus omega or omega kg minus omega. So the sinc function is only large when its argument is about 0. Okay, let's go back here then. That means that this second term is going to be big if omega is about omega kg. And this other term is going to be quite small. Okay, so the our final answer then is that B tilde of omega kg is approximately sinc of omega kg minus omega t over pi so of course really interested in is that over h bar squared and then we have our constant. Let's see, I should call it V0 just to remind ourselves that's the remind ourselves that's just the amplitude that we're holding constant, and so we get this classic relation, and we actually have a factor 4 from this 2 squared. Okay, so once again we get our sinc function, but now it's peaked at omega kg, And so the probability of the system being in state K is the sinc function of omega minus omega kg. And so we see from this, this Bohr condition is going to be E sub k minus E sub g approximately equal to h bar omega, energy conservation, or equivalently the Bohr condition.